Good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about tensor operations. So in this lecture today we'll talk about the operations involving vectors and tensors, and this will give us lots of practice on indicial notation. So let's get started. So the first product we'll talk about today is called the tensor product. The tensor product is also called the outer product. Right, so if we have two vectors u and v, their outer product or tensor product is simply written as u times v. So please note that notation wise there is no dot or no cross here. We just write a u and followed by a v. So if I was to use the indicial notation, this would be ui ei times vj ej. And if I move the scalar components to the left, so this becomes ui vj followed by ei ej. So now the question is, what exactly is this? We are used to having just one e hat, like ei hat, which would expand typically to a vector if you write all the components. But what exactly this quantity where you have ei ej without any dot or a cross in it? In fact, this is the tensor product or the outer product of the unit vectors ei and ej, and this is called the dyad of ei and ej. So the quantity ei ej is called the dyad, and when I say ei ej, that is the outer product or the tensor product of ei and ej. So let's expand the expression, because as you can see in this expression we have repeated indices. You have ui ei and then you have a vj ej. So if I was to expand this by doing a sum over the indices I and the indices j, this would expand to a total of 9 terms added together. So let's write them down. So we can see there's a sum of 9 independent terms here, and this looks very much like a second order tensor, because in a second order tensor you have a total of 3 to the power of 2, that is 9 terms. So this has 9 terms, 9 mathematical terms in the expression, which gives us a hint that this is a second order tensor which has 3 to the power of 2 terms in it. And if you compare this with typically a vector would have 3 terms, something times e1 plus something times e2 plus something times e3. Here we have something times e1 plus something times e1 e2 plus something times e1 e3 and so on, all the way to something times e3 e3. So this definitely tells us that these combination of unit vectors e1 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 e2 e1 e3 and so on, they are the basis of a second order tensor like we had in a vector. So I can say E1 E1, E1 E2, E1 E3, E2 E1, and so on all the way to E3 E3 are the bases in a second order tensor. So with that logic, we can say that any second order tensor can be written as a linear combination of these 9 basis components. We also note here that the bases E1, E2 and the bases E2, E1 are different. So they are not equal. So they're different bases. So what that means is that the outer product of E1 and E2 or the outer product in general is not commutative. This is an important point because sometimes we confuse this like in dot product, which is commutative, but the outer product is not commutative because the because the basis E1 E2 is not equal to E2 E1 and so on. So they are not commutative, they are different bases. Now sometimes, just to avoid notational confusion, we write the outer product or the tensor product of uv explicitly as u times v. So rather than not using any symbol, we use a cross with a circle around it, which is a symbol also used for outer product. Now in this course, while writing the outer product, we will not use this cross with a circle symbol, but some books do that because sometimes it is confused with a slight dot that may appear in the print. So this is called the outer or tensor product of u and v, and the quantity uv is called the dyad of u and v. So this quantity uv is called the dyad. Why do we call this outer product a tensor product? Well, that's because you started with two vectors u and v, and that gave you as a result a tensor which was a second order tensor. So this is the reason that we call it a tensor product, because you end up getting a tensor of higher order by combining tensors of lower order. In this case, we are showing a vector, but as we'll see later that this tensor product can also exist between tensors of higher orders. But for now, let's stay with the dyad of two vectors. So I can also write that uv is not equal to vu for the same reason that the outer product is not commutative. So I'll be using the word outer product, tensor product and the dyad of two vectors interchangeably, and I would really want to do it so that you get used to these terms. Many of you may be seeing this outer product of two vectors for the first time. Till now, we were only used to two kinds of products between vectors, either the dot or a cross product, but this is something new for us. But that doesn't mean that this is not used. It is very much used in the field of continuum mechanics, and that is the reason we are studying that as a part of this mathematical background in the course. So you will see that it is useful, and it is definitely very popular as well in continuum mechanics. Okay, now that we've been using the word outer, let's also clarify the word inner which we have used in the past and compare the two. So the inner product between two vectors u and v is written as in the symbolic notation as u dot v, and we know that when we do that, what we get is a scalar. If we write in the indicial notation, this is ui vi, so this expands to u1 v1 plus u2 v2, sorry, plus u3 v3, which is just a number. So this is a scalar, and scalar is a 0th order tensor. So we will see some sort of a trend here or a pattern here, and then we'll try to generalize. So u is a first order tensor or a vector. So I'll say order 1, first order. V is also a first order, and when we did an inner product between the two, we got a 0th order. So I can write some sort of an equation which says 1 plus 1 and then a minus 2 equal to 0. So what we are doing here is that we are taking the input tensor orders, so which is 1 plus 1, because u was order 1, v was order 1, and then you add them. But when you do an inner product, the inner product results in a minus 2. So these are input tensors. This minus 2 is because of inner product, and this is the output tensor. Of course, we're talking about orders here. I will talk about this in more detail in later this week, but for now, let's remember that we have a pattern here when we talk about inner products. Now, the inner product is also represented as matrix, in matrix form. So let's write the matrix representation. So in the matrix representation, we write u1, u2, u3 as a matrix which is 1 row and 3 columns, and then we write v as v1, v2, v3 as a column vector which is 3 cross 1, and when you multiply this, you know that you get just one element which is u1 v1 plus u2 v2 plus u3 v3, which agrees with this 1 by 1. That's from matrix multiplication. So the inner product between vectors u and v, which is basically the dot product of u and v, that is u dot v, is represented as u written as a row matrix, v written as a column matrix, and we get a single scalar term as a result. So let's now move on to the outer product. So in case of outer product, as we have just seen in this lecture, that is written symbolically as u times v, this is a first order, this is a first order, and this results in a tensor of second order. Okay, so this is second order. So let's write our the pattern that we notice here. So 1 plus 1, this is because of the input tensors, is equal to 2. That is the output tensor. So we see that there is no minus 2 here, because the minus 2 happens because of an inner product in the orders. Since there is no inner product, it's an outer product, so the input tensor orders simply get added and we get a second order tensor as a result. So let's go back and compare with the inner product. So inner product we had -2 here, but that is not there in the outer product. Let's also look at the matrix representation. So in this case, we will write U as column vector, which is 3 rows and 1 column, and we'll write V as a row vector, which is 1 row and 3 column. So when you multiply a 3 by 1 matrix with a 1 by 3 matrix, you will get a 3 by 3 matrix. So you have U1 V1, U1 V2, U1 V3, and so on. Right, and this agrees with the 9 terms that we had. So let's go back and have a look at the sum of the 9 terms that we had here. As you can see, so these 9 terms are exactly what we have, except that we are simply writing the components. We are not multiplying them by the basis vectors and adding like you do in vectors, where rather than writing u1 e1 plus u2 e2 plus u3 e3, you simply write the vector as u1 comma u2 comma u3, or simply as a row vector u1 u2 u3. So let's move on to the next kind of product. So this product is called the vector-dyad product. So what we're doing is we are multiplying a vector with a dyad, and the dyad is something that we already have just defined. So, but in fact, vectors and dyads can be multiplied in different ways. So we'll have subsections here. So the first way we'll multiply a vector u with a dyad, which is a dyad of two vectors v and w, is using a dot product, that is an inner product. So again, these things will be very new to many of you, seeing a product between vector and a higher order tensor, that is a dyad, and then the products can be of different kinds. Alright, so this is a first order tensor and this is a second order tensor, because it is a dyad of two vectors, as we have just seen. So let's write in the indicial notation. So the way this product is defined is that you take the dot product between adjacent terms or the adjacent vectors. So in this, if you look at the left of the dot, you have an EI, and to the right of the dot we have an EJ. So the dot happens between EI and EJ. So I'll move all the scalar components, that is UI, Vj and Wk, to the left, because they are simply scalar components. They can be moved to the left, and then we are left with is EI dot EJ, and then we have an EK remaining. Remember, don't move around the vectors, because the order in which the vectors appear is also important here. So just to be safe, if EK is to the right of EJ, it stays as it is. So this, from the definition of Kronecker delta, is so EI dot EJ is delta EJ, and then we apply the substitution property, which results in getting rid of the J in the term. So you have a UI, VI, WK, EK, and we can see that this whole thing is nothing but a vector, that is, it is a tensor of first order. So let's write our pattern here in terms of the orders. So what we started with is this equation which had a u dot vw. So let's write it again, u dot vw. So this was first order, this was second order, and what we got as a result was a vector which is a first order. So our equation is 1 plus 2 minus 2 is equal to 1. So this 1 plus 2 is the input tensors. This final one is an output order of the output tensor, and this minus 2 is because of the inner product. Right. In fact, if I had to complete this equation here, if I go back from the indicial notation to the symbolic notation, I have a UIVI, which is basically a U dot V. So remember, we are learning to go back and forth. So U dot V, and then a WKEK is simply the vector W. Just to write the complete equation in the symbolic notation. Now, many of you may be thinking that where in the world would we get things like dyads or things like a dot product between a vector and a dyad. Now again, as I said, these are quite common in continuum mechanics. So I'll give you a quick example on what kind of work in terms of dealing with equations in continuum mechanics would result in these quantities. So let's deviate a bit and take an example. So let's say you have an equation like dw by dt, where w is a quantity which depends on the independent variable time, a vector quantity which depends on independent variable time, times alpha w is equal to 0. It's a very common equation you would see in mechanics. So what we do is, well, the right hand side is a 0 vector, by the way, but I'm just writing a 0. So what we'll do is we'll multiply both sides by the vector v. So this becomes v times dw by dt plus alpha w is equal to still a 0. And when I move that v inside, what we'll get is d. Let's say v is not a function of time, so this becomes d of v times w upon dt. Now this v times w is nothing but the dyad of the vectors v and w plus alpha vw, because we multiplied from the left, so it becomes a dyad like this. And now it may happen that we may take a dot product on the left hand side with a vector u. So this will become a d by dt of, well, let's say u is a function of time, so we don't move it inside, so it's u dot d by dt of vw plus alpha is simply a scalar, then u dot vw, and this is equal to a 0. So you can see that by playing around with the equation, by multiplying it with different terms, we get these terms where we have a product of a vector and a dyad, that is an inner product of a vector and a dyad. And again, if you look at equation of fluid mechanics, for example, when you write the momentum equation in a general vectorial form, you do get these terms. Or when you work in turbulence, where we deal with the derivation of the turbulence kinetic energy or turbulence dissipation rate or some other higher order turbulence parameters, then we get these kind of multiplication between vectors and dyads and so on. So this, as I said, it's quite common. You will see that in advanced courses in continuum mechanics. So don't assume that this is just for theoretical purposes. It is very much used. Right, so let's go back to our work that we were doing. So we just talked about one kind of product between a vector and a dyad, that is a dot product. So let's talk about another kind of product, which is the cross product. So U cross VW. So let's go into the indicial notation. So this is UI EI crossed with VJ EJ times WK EK. Again, the cross happens between adjacent vectors EI and EJ. So first I will move all the scalar components to the left. So UI VJ WK, and then we have an EI cross EJ, and then we have an EK. Okay, again the ordering matters. Make sure EK stays to the right. Okay, so this is what we get, and now as the trend is, I'll move the epsilon to the extreme left. Then we have a UI VJ WK, and then we have the vectors EQ and EK. Now what is EQ EK? This is nothing but the outer product of EQ and EK. That is the dyad of EQ and EK. So this looks to be a second order tensor. So whatever the output of this cross product was, a second order tensor. This whole thing. So let's write the pattern. So the input was a first order. This was a dyad of vectors. So this was a second order. And the output is a second order. So in this case, our equation does not work because we neither have an outer product and neither we have an inner product. So this is a different kind of product. So the input is 1 plus 2 and the output is some 2. So we have a minus 1 here. That's what the vector, in this case the cross product, results in. Right, so this was a product between vector and dyads. So if we can have a product between vector and dyads, why don't we have product between dyads and dyads? So let's do that. So 3 is a dyad product. So again, the first kind is UV dot WP. So we have two dyads, UV and WP, and we take a dot product between them. So let's write in the indicial notation UIEI VJEJ dotted with a WKEK and EQEQ. So in this case, the dot happens between adjacent vectors. So this becomes UI. So let's move all the scalar components to the left. So UI VJ WK and PQ, and then we have, let's follow the order. So we have an EI first, and then we have a delta JK followed by an EK. So let's check again. We have UI VJ WK PQ, which are the scalar terms. Then we followed the order from left to right. So EI, then EJ dot EK results in a delta JK, and then we have an this should be PQEQ. So this is an EQ. Right, so what we can do further is we can apply the delta substitution property. So this becomes equal to UI Vj, Wk, Pq, and since we are applying the substitution property of delta, so we'll replace the index k with an index j. So the index of W becomes Wj, and then we have an Ei and Eq in the same order as we had above. So we can see that from the bases in this expression that this is a second order tensor. So let's check the orders. So in the input we had two dyads, UV and WP. So the orders were 2 plus 2, and in the output we also have a second order tensor as we just saw. So the order is 2, but because of an inner product, that is 1 dot, we got a minus 2. So this 2 plus 2 is input tensors or dyads. The output order is here, and this minus 2 is because of an inner product. Now let's talk about another kind of dyad-dyad product, which is called a double dot product. Now this definitely is something very new. We've been talking about dot product, which is we just put one dot, but we can also put two dots here now. So let's look at it. So we have vectors u and v, and the dyad of u and v, and then we have a dyad of w and p, and we put two dots like this horizontally. So this is called a double horizontal dot product. So we have a second order 2 plus 2, so that's the input order because we have two dyads in the input, and we have two dots, so that means there's a minus 2 minus 2. So this minus 2 and minus 2, this is because of two inner products. So the output should be 0, right? And this is indeed the case. So let's look at the definition of the double horizontal dot product. So if you have ui vj, so you'll have a w, and then this will be a j, and you'll have an I here. Okay, so this is the definition. So again, there's no need to fight this because this is a definition. This is how the double horizontal dot product is defined. Now if you want to compare it with a single horizontal dot product, so in single horizontal what we did was we did a dot between these two. Okay, so this was a single dot product. So when we bring in a double dot product, we also do a dot between this and this. So when you do that, I'll write it very quickly. So when you do a dot product between EJ and EK, all you end up with is a VJ WJ. And when you do a dot product between EI and EQ, you end up with a UI PI. So I just move this PI here just to maintain the same ordering. So I get a PI. So this is the same as what we had here. Alright, so this is the definition of a horizontal double dot product. Again, this is not as arbitrary as it may appear at this stage, but we'll see that later when we start using these products. Now the third one in the category of dyad-dyad product is the vertical double dot product. So we'll call this the double dot product vertical double dot product. So again, this is a definition. We don't have to fight this. So in the definition, what we have is, we have, so in the horizontal one, we did a dot between this and this. So here what we'll do is, we'll do a dot between V and P, and then a dot between U and W. So if I write maintain the orders as it is in the initial notation, although that's not required in initial notation, I have a UI Vj, and then I have a Wi Pj, because V is dotted with a P and U is dotted with a W. So their indices have to be the same. Okay, so this is the vertical double dot product. In the symbolic notation, this is written as U dot W times V dot P. Now just one more thing before we close this lecture today. The ordering of scalar components in the indicial notation is not, or does not matter. What I mean to say is that Ui Vj in the scalar components times Ei, let's say Ej, I can also write this as Vj Ui Ei Ej, because these are simply scalar components here in this representation. I cannot change the order of Ei Ej, because that represents an outer product between the bases, and I know that outer product is not commutative. But since Ui and Vj simply denote scalar components of vectors, so they can be rearranged, the answer is still the same. So be very careful that don't rearrange the basis components, but you can rearrange the scalar components. So let us summarize today's lecture now. So today we learned about tensor operations, particularly operations which involve vectors but result in tensors, or which involve tensors of higher orders like dyads or vectors, which is order 2 tensors resulting in tensors of various orders. Okay, so the input and output were tensors of different orders. So we started with the definition of the outer product, also known as the tensor or the dyad of two vectors. So we talked about the outer product. This helped us construct a dyad, and then using that we worked with some different kinds of vector dyad products, and we also dealt with dyad products. So I gave you some practice of indicial notation, and at the same time I defined some products of different kinds, and also showed you a pattern equation where every dot or every inner product results in a -2 in terms of order, and in the outer product there is no -2, so the orders simply add as expected. So that is the end of this lecture. Let's have a look at some food for thought. So the first question for you to think about is that, is the dot product between the vector u and the dyad vw is the same as uv, the dyad uv dotted with a w. Okay, so this is where we test the associativity. Is that true or not? So you will have to think about it. In fact, the way you can do is you can expand this using indicial notation, take the dot between adjacent terms and see what you get as an output, and compare that with what we got today. The second FFT again is to check if the cross product between a vector and a dyad is associative. So thank you very much, and I'll see you in the next lecture.